So when we're talking about balanced chemical equations, you should know that everything that's on the left-hand side is considered a reactant. When I say left-hand side, I mean to the left side of the arrow. And everything to the right-hand side of the arrow is called a product. And this just says the same thing. Now, why do we balance a chemical equation? If we look at this example, we see iron, oxygen, and it forms iron oxide as a product. Now, at the microscopic level, actually below the microscopic level, we have 4 atoms of iron react with 3 molecules of oxygen, and it forms 2 formula units of Fe2O3. Now, we can't really see what's going on at the submicroscopic level, but we can say this, that 4 moles of iron reacts with 3 moles of oxygen to form 2 moles of iron 3 oxide. And if we were to convert the number of moles into grams, we would get this, 223. And I got that by taking the mass of iron per mole times 4. This is the mass of O2 times 3 right here. And the mass of Fe2O3 times 2 is what I have right here. 223.2 plus 96 does equal 319.2. And this shows the law of conservation of mass. And that's why we balance equations. Which of the following correctly balances the chemical equation given below? My suggestion is that you pause for a moment and see if you can determine which one is correct, or which ones, or maybe more than one, that's balanced correctly. Now, the ideal way to balance a chemical equation is with whole number integers, but you could have multiples of those integers or fractions of those integers and still have it work out. But when we balance it, we would typically have whole numbers. Here are the correct answers. Okay, so why doesn't one work? Please think about that one. Here's another example. Which of the following are true concerning balanced chemical equations? There may be more than one true statement. Okay, so the number of molecules is conserved. That's actually not true. Molecules doesn't have to be conserved, so this one is false. The coefficients tell you how much of each substance you have. That is true. Atoms are neither created nor destroyed. That is true. The coefficients indicate the mass ratios. No, that is false. The coefficients indicate the mole ratios. When the sum of the coefficients on the reactant side equals the sum of the coefficients on the product side, that is also false. It may happen, but it's not required. The coefficients do tell you how much of each substance you have also, but not in grams. It tells you how many moles. That one actually should be true as well. It tells you how many moles. I'll be more specific here. All right, so the number of atoms of each type must be the same. You cannot change subscripts. It tells us the ratio of molecules, which is also the mole ratio. And you can use fractions, but we would prefer to use whole number integers. All right, here are the steps for a stoichiometry calculation. You have to have a balanced equation. You have to convert your given into moles if it's not already in moles. Then we are going to use what's called a mole ratio. I'll show you these. And then you convert from moles of the new substance into whatever unit is required of you. Let's look at an example we can do in our head. Okay, so here we have a balanced equation. There are 2 examples here. So we have example 1 and 2. Let's just look at this top one right now. This is a 1 to 5 to 2 mole ratio. I'm using that based on the coefficients in the equation. So in this given, if I have 10 moles of oxygen, how many moles of phosphorus would I need? And how many moles of diphosphorus pentoxide would I need? So I notice that 10 is twice of that of 5. So then what's twice 1? That would be 2 moles of phosphorus. And then here, twice of 4, or twice of 2 would be 4 moles of P2O5. And the goal is that we still keep the same simplified ratio. 2 to 10 to 4 is the same as 1 to 5 to 2. Now let's look at this new example. Let's say in this given, we have 3 moles of phosphorus. How much of oxygen would I need, and how much product would be involved? So 3 is triple the original amount, which was 1. So then I'll triple 5, which would be 15. and I'll triple 2, which would be 6. Now I've picked examples that I can do in my head, but what would the work look like if I had to show the work? So we want to find out how much of these other substances we would need to go along with what's given here. 1.75 moles of P2O5. Again, this is the same reaction from before. Now I'm going to first find out how much of phosphorus I need to react with this. So I'm going to start with my given 1.75 moles of P2O5. I want to find out for every amount of P2O5 I have, how much phosphorus would I need. And I look at the numbers that come from the balanced equation. There's a 2 in front of this, and I'm going to put that right here. There is a 1 implied, and I'm going to put that right in here. So this is what's called a mole ratio. So again, a 2 from here and a 1 from in front of phosphorus. Moles of P2O5 cancel out, and it's 1.75 times 1 divided by 2. And then you see that the answer is 0.875 moles of P4. All right, now what about the amount of oxygen? I'm going to do the same kind of a calculation here. 1.75 moles of P2O5. The relationship between P2O5 comes from the balanced equation, P2O5 and oxygen. It is a 2 to 5 ratio, 2 of these to 5 of these, and then that cancels out. So this is how I would solve. I'll take 1.75 times 5, and then I'll divide it by 2. And the answer is 4.375. And because of significant figures, it can only have 3 digits, so it's 4.38 moles of oxygen. I'll write that in here, 4.38 moles of O2. Now remember that this was a 1 to 5 to 2 mole ratio. Now even though these numbers are different, if we were to simplify them, it would also have a 1 to 5 to 2 mole ratio. Here's a little diagram or an image that I use sometimes to think about my work. So you might want to pause the video here and draw this in your notes. This is how we convert, the steps to convert from grams of what I would call the given. So these are all in yellow, what we are given. And I don't know if you can even tell that that's yellow, but that's what this is supposed to be. Yellow here, 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 and here. So this is the substance that's given in the problem. Now we're looking at the next example. So what we're trying to find is in green. All right, what we're always linked by is the moles of the given converted to the moles of the product. We use a mole ratio, and that's what really makes a calculation a stoichiometry calculation. Here's an example balanced equation, and it says how many moles of ethanol are required to produce 58 moles of CO2. First step is to have a balanced equation, and that's done for us. The second step is to convert your given into moles. Our given here is 58.0 moles of CO2. So we don't have to convert it to moles because it already is in moles. Next, I'm going to convert from moles of what I have, CO2, which it says 58 moles. And I'm looking for moles of ethanol. This is ethanol. And I'm looking for the amount of moles of this. We don't know that right now. I'm going to put what I know right here, moles of CO2 in the bottom, and what I need, which is moles of C2H5OH in the top. And it is a 2 to 1 mole ratio. CO2 cancels out. And 58 divided by 2 is 29. Of C2H5OH, and that's our final answer. Let's do another example. Here's a familiar reaction that we've seen before today. And now it's saying if we have 6.25 grams, so here's our given, 6.2 grams of phosphorus. I'm going to write that in right here. Okay, that's the substance that's given for us. What mass of oxygen does it combine with? I don't know. I'd have to find out. Okay, so the first step is to have a balanced equation. We already have the balanced equation. Second step is to convert the given into moles if it's not in moles. Okay, it's not in moles, so I need to do that first. So I'm going to take grams of phosphorus, put that on the bottom, moles of phosphorus, put that on the top, and this is 1 mole of P4. So this is a special form of phosphorus where there are 4 atoms combined together into 1 molecule. The mass of a phosphorus atom is 31. You take that times 4, so it's 124 grams per mole. That cancels out. The next step is to convert it into the substance that we're looking for. Well, I'm looking for oxygen. So I'm going to take moles of P4, which is what I had right here. I put that on the bottom so it will cancel. Now I convert to moles of O2. The numbers that get plugged in here come from the balanced equation. It's a 1 out in front of phosphorus, and it's a 5 in front of oxygen. This step is called the mole ratio, and you have to have a mole ratio in every single calculation that you do in stoichiometry. That's required. The last step is that I'm looking for grams of oxygen, and right now I have moles. So I'm going to put moles in the bottom to cancel out. Grams in the top is what I need. 1 mole of oxygen is 32. It's 16 for each times 2, so 32 grams per mole. Moles cancel out, and my calculation looks like this. I multiply everything in the top. 6.25 times 5 times 32. 6.25 times 5 times 32 divided by 124, and my final answer here is 8.06. I have 3 sig figs here, 4 here. The mole ratios are exact, and 3 there. So 3 sig figs, that's grams of O2, and that's my final answer. Next example. It says, again, 6.25 grams of phosphorus. Well, this looks familiar. That's our given. 6.25 grams of phosphorus. And then it says how much product, which is this one, is formed. So that's what makes this example different, because we're converting from grams of one thing to grams of another. So it's 6.25 grams of phosphorus. We want to convert from grams of phosphorus into moles. And if you remember from the last example, we knew that it was 124 grams per mole. So grams cancels. Now we go from moles of phosphorus to moles of P2O5. And from the balanced equation, there's 1 mole here to 2 moles here. Okay, then the last step is to convert from moles of P2O5 into grams of P2O5, because that's what the question asks us for. 1 mole has, let's see, I'm adding these up now, 142 grams per mole. So I multiply everything in the top, and I divide by 124, and I get 14.3 grams of P2O5.